Okay, so you might be thinking, why do acids and bases even matter? Why do I need to know these definitions? And so one answer to that question is that many of the chemicals we use in medicine for treating diseases are acids or bases. In fact, most of them are. Sometimes they're based on ammonia, which we saw on the last slide is NH3. Now the conjugate of ammonia, so what it would form if it reacts with water, would be something where this has a lone pair of electrons, and so it's going to steal a hydrogen. So the hydrogen goes from water to NH3, so you get NH4 plus and hydroxide. So ammonia is actually a base because you made OH minus. Okay, so if that's true, a lot of the drugs we use are based on ammonia or ammonium. That's the NH4 right here. That classification of drugs are generally named amines because it's similar to ammonia. It's derived from ammonia. Amines don't dissolve very well in water. And since people like to take drugs by eating them rather than injecting, you need to be able to dissolve your drug in water. All right, so here we have an amine group, right here. This is based on ammonia because it's got a nitrogen and some stuff attached to it. And we have another one over here. So this is the same compound. It's just that the one on the right has an associated acid with it. So if this compound, which I think is phenylephrine, an allergy medicine, if this compound does not dissolve in water, what we can do is kind of attach it, react it with some acid. So bases and acids like to react. And when they do, they form a salt. And so this salt will dissolve in water. Okay. So when you see chemical labels like on the back of a medicine package that say HCl after it, what that means is that the original medication that is actually going to help people is a base, probably an amine, and they need to react it with HCl so that it'll create a salt that dissolves. Okay, so these reactions have direct application to your future work in allied health field. All right, so the different types of reactions, this is just sort of a reference sheet for you. The different types of reactions for acids are outlined here. Sometimes they make hydrogen gas. We call that a single displacement reaction, so we've seen those before. Other times it reacts with an acid and a base together, so if you do that, it always produces H2O, which is water, and a salt. Not a salt like a salt and battery, but like ionic stuff. I know that was funny. I'll give you a second to laugh. Okay, so the next kind of reaction is if we take acid and react it with what we call metal oxides. That's literally compounds where you have a metal and an oxygen. So this Fe2O3 is rust. It's actually, I think, the red rust that you might see on your car after a harsh New York winter. If you took some HCl and poured it onto your car, it would react with the rust to remove it. It would actually create this substance, which is aqueous. It's called iron chloride. The downside to doing this is you're actually removing iron from your vehicle, so you're sort of impacting its structural integrity a little bit. And then the final reaction is what happens whenever you take some acid and react it with a carbonate. So carbonates are anything with that CO3 group in it. This is a kind of double displacement. So initially, we're going to switch the cations to get NaCl. That's a salt, so the Na and the Cl pair up. And then we're gonna take the H and pair it up with the CO3. Now CO3 actually has a 2- charge, so that means I gotta have 2 hydrogens to attach to it. Okay, so I make H2CO3, and I've separated these oxygens and colored them so we can see where they go. Because carbonic acid, that's this one, is famous for doing this reaction, where once you've made carbonic acid, it's very unstable, and it will immediately fall apart to form water. So one of the oxygens goes onto water, and CO2. The NaCl is still there, so we're going to rewrite that again. But the final answer, the final like mixture is sodium chloride, water, and carbon dioxide. All right, so the next classification of compounds I want to talk about is called amino acids, and you might have heard these before if you're a weightlifter or somebody who's interested in increasing protein intake. If you look on the back of a protein shake, it's going to list a whole bunch of names like lysine and guanine and just a ton of INE ending names. Those are amino acids, and the function of an amino acid is to make all the proteins and enzymes in your body. And they do that by having a really interesting chemical property. All right, so the first thing is we've got those amine groups here. So this is an unpaired pair of electrons on the nitrogen. And so that makes this, the amine, the ammonia-based thing, is a base. On the other hand, we also have another part of this molecule that is called an organic acid. And we've seen this kind of thing before when we were looking at acetic acid, right? So that has this same kind of structure. C double bonded to an O, which is also attached to an OH. So this hydrogen on the oxygen there is very reactive. It's very acidic. And so it's going to sort of be kicked off pretty easily. So that means that this amino acid structure has both a region that is a base and another region that's an acid. And this is very handy because what it does is it has the ability to take one amino acid and form a connection to the next one, because if you have, our black represents an acid and our red represents a base, when you have an acid and a base, they can form a bond by releasing water. Okay, so this would make a long chain. You keep going down like this, you keep making connections, and proteins are really long chains of amino acids, like hundreds and hundreds of thousands of amino acids attached together. When they attach like this, we call this a peptide bond. It just means protein bond. And a peptide bond is like making a salt. Okay, so when we had salts before, when you do an acid-base reaction, you produce water and a salt. And so here the salt is the protein you're trying to make. All right. So the answer to the question is an amino acid an acid or a base. The answer is that it's actually both an acid and a base in different parts of the atoms of the molecule. So lots of things can be both an acid and a base, not just amino acids. And when they are, we call them amphoteric. That means capable of being an acid or a base. The decision about whether to act like an acid or a base is made based on what else you pair it with. So for example, zinc hydroxide, ZnOH2, is very good at being amphoteric. So if I put HCl in with my zinc hydroxide, it'll make ZnCl2 and H2O. If, on the other hand, I put a base in, such as KOH, it is going to form a completely different compound with completely different properties, different color, different, solubility, different everything. It's a totally different compound. Okay, this would only work if you used a strong acid. And so that begs the question, what are the strong acids? And I'm going to review that here in a minute, but we already know that strong acid means that it is a strong electrolyte. Right? So this leads us to a review of our discussion from the laboratory about electrolytes, and we got to remember that electrolyte means to conduct electricity by untying yourself. The language we use to describe that process is that the substance either dissociates or it ionizes. You can kind of use those two interchangeably, although we tend to say dissociate when talking about acids and bases, and ionize when talking about ionic compounds. It's not totally required. There is some sort of fudge factor. People will still understand what you're saying if you always say dissociate or ionize. But the two terms do exist, so I wanted to make it, bring it to your attention. Okay. So, we remember from lab that when something produces more ions, like NaCl would produce 2 ions, but calcium chloride would produce 3, that results in a brighter light, or you can think of it as more energy. Okay, so NaCl would create 2 particles. CaCl2 would, of course, create 3 because there are 2 chlorines and 1 calcium. So that means that CaCl2 would have more light than sodium chloride would. That's because they're both strong electrolytes. So it goes and forms 100% Na+ for every NaCl that is put in, like that. Acetic acid is not a strong electrolyte, it's a weak electrolyte, and that means that only very rarely does H+ form. Okay, we learned in the last chapter that if I had, I think, 1 molar acetic acid, only about 0.004 molar H+ forms. So it's a very small amount. Okay, I want you to go into the lecture and click on this picture. You got to open the lecture like as a presentation and then click on the picture. And I want you to tell me, what is something the cat says? You don't have to tell me everything he says, just maybe one of the phrases. Okay, so in review, we know that the Bronsted-Lowry definition of acids is that they are proton donors. The base definition is they are proton acceptors. And I want to add that the Lewis definition is kind of a little bit opposite in a way. So Lewis said that acids are electron acceptors, like Fe3+ accepting the electrons from cyanide, and bases are Lewis electron donors. Okay. So we can arrange the acids and bases by how strong they are. And so on the left side of this figure, we have a lot of acids listed from the strongest down to the weakest. The bases go the opposite direction here. The strongest ones are at the bottom and the weakest ones are at the top. In the regions between water and the end of each one, those are strong acids on the top and strong bases on the bottom. That means that they would completely fall apart. Every HCl molecule in that sample forms chloride. From the water, which is right here, all the way down to the next water, so water's on here twice because it can be both an acid and a base. But in between the two waters is all the weak acids and bases. Now this doesn't actually list every single one of them, there's millions, so it couldn't. But it does give us the most common ones. And so to figure out if something is an electrolyte, I need to ask myself, is it the question, is it ionic? If the answer is no, then I want to see, is it on the chart to, is it an acid or a base? If it is, then it's an electrolyte of some sort. If it is not, then it's probably a covalent compound. So let's see, glucose, they give us the formula there, it's kind of like sugar. Glucose is not in the acid-base chart at all, so I'm going to guess this must be a non-electrolyte, since it's not on the chart and it doesn't have a metal in it to be ionic. The next question is definitely ionic, so let's think. That must mean, I'm assuming this dissolves. I could go back to my notes from the last chapter with that table to see, but I remember that chlorine is usually soluble, except when I mix it with silver, mercury, or lead. Okay, so if this is ionic and it's soluble, that means it's going to form its ions when you put it into water. That means it's going to be an electrolyte, and if it is ionic, it has to be a strong electrolyte. We didn't see any weak ionic compounds. All right, so the next one is H2SO4. I found HSO4. Oh, so H2SO4 is right up here on the top. it is in the strong acid category, so that means it is also a strong electrolyte. With NaOH, that one's hidden because it's actually related to this OH right here, and the fact that Na is always soluble with no exceptions. Okay, so I want you to finish the last two and bring them in.